Hello everyone, welcome to the lecture 5 of Vector and Kinematics series. So myself Subhajit. So today I will be defining how to define the velocity and acceleration with the vector formalism we have developed till now. So till now we have developed the basic foundation of vectors, that is how do you add and subtract and to vector, and then we have discussed how to define the dot and cross product of vector. After that we have defined how to disintegrate a vector component wise and define and calculate the cross and dot product with that component. And then based on the first three lectures we have discussed few problems regarding the dot and cross product and basic foundation. So till now we have only discussed the mathematical formalism, and we have not discussed any physics on the application of vector on physics. Today I'll be starting with the velocity and acceleration. Now let us define velocity and acceleration in terms of vector. So for a body in one dimension, if this x-axis denotes the time coordinate and y, and this axis y-axis denotes the x coordinate. So if it moves from this point to this point at time from t1 to t2, and if the position vector of this is x1 and x2, that is, this has two following coordinate, that this point has coordinate, let's say A is this point and B is this point. This point has coordinate x1 t1 and x2 b has coordinate x2 t2. Then the velocity is x2 minus x1 by t2 minus t1, right? That is x at t2 minus x at t1 by t2 minus t1. Fine. Now if I let's say t2 is t1 plus delta t, that is that distance is delta t. Now then what is v? V is x of t plus delta t minus x of t by delta t. Now if I assume this delta t is almost tends to 0, then this v is limit delta t tends to 0 x of t plus delta t minus x of t by delta t. So that is basically the derivative of x with respect to t. So in one dimension, if you have any zigzag motion like this motion, then this defines the tangent to the curve like let's say you have at this point, and you need to evaluate the velocity vector of that, and for that you need to draw a tangent to that curve and evaluate dx by dt at this point. That will be that dx by dt at this point is the magnitude of that velocity, and the direction of velocity is basically the tangent to the curve, the direction of tangent to the curve. Here if you want to evaluate the velocity, then this is the velocity direction is along this direction, and the derivative along this and in this point is the magnitude of velocity, and here it is directed along this, here it is directed along this, here it is directed along this. So the velocity vector changes here all the time. Now in the same fashion, the rate of change of velocity is the acceleration, and that is defined like dv of dt, that is d by dt of dx by dt, that is d2x by dt square. Now what about in the three-dimensional case, or in any dimension? So if you denote the t vector here and a and r, the position vector of any body is here, with r is the short form of x, y and z. Let's say you have time here, and let's say you have a four-dimensional space here, that is t, x, y, z. Your time is along this axis, and in another three axes you have x, y and z. The axes are orthonormal to each other, that is the angle between t and x, the angle between each of the component here is 90 degree, right? So, and we are denoting the short form of that version as r. So if the body in here has direction of at this point, if this has a position vector, let's say if the body is here and it has a position vector r of t, right, and in delta t time it moves along, let's say delta r, right, in time delta t, and that is this thing is r, that thing is delta r, and this thing is t, and this thing is delta t, right? Now, so what about this vector? So what is this thing? This is basically the position vector of that particle at time t plus delta t, that is r of t plus delta t. Now if I want to evaluate that r of t plus delta t minus r of t by delta t, like the previous scenario, that is basically defines the velocity. This minus this position vector of this minus position vector of this by the time taken to reach that point is the definition of velocity, right? Here then this is just, if I take then delta t tends to 0, then limit delta t tends to 0, if I take then r of t plus delta t minus r of t by delta t is basically dr by dt, right? So which is equivalent to, if I break this component wise, this scenario component wise, that is basically you have time t, if you have x, the body that that is at time t it has coordinate x, at time t plus delta t it has coordinates x plus delta x and t plus delta t, right? And here this vector is basically x of t plus delta t. Similar situation in the y coordinate also. If you plot t with y, this is yt and this is y plus delta y and t plus delta t and this is y of t plus delta t, right? And this length is y of t plus delta t. So now y of t plus delta t is basically, if you take the projection of this into here, it will give you y of t plus delta t at time t plus delta t. That means so if you take again the meaning of this is if you take the combined coordinate x y, then this delta r is basically, if you take the time, if you take the projection of it here in the x-axis is delta x, if you take the projection here it is f of t plus delta t, if you take the projection here it is y of t, if you take the projection here it is y of t plus delta t, right? Now similar for yz and zx axis. So if you break this vector relation in component wise, if you want to take a closer overview, so you will get all this merging views, right? So these are all the merging views. So in short, this is the advantage of vector. You can denote this plenty of notation, plenty of all the notation in a short form, like v is just dr by dt. Instead of telling the component of x of v along is dx by dt, component of y is dy by dt, and component of z is basically dz by dt. You can combine all the, if you have all the other, if you have beyond x, y, z, if you have other coordinates, you can combine all them together and form a single equation like d is only equals to dr by dt. This is the most advantage of vector, using vector. Like, so these are the things. So similarly, the acceleration a is defined as this dv by dt, rate of change of vector. And by the way, these equations are valid in any dimension. This is we can imagine only 3 dimensions, but this equation is actually valid in any unphysical dimension, any normal, any d-dimensional space where d is any value that is 4, 5, 6, and beyond that any value. And these equations are valid in any dimension. these are the advantage of vectors. So again, A is represented as dv by dt, that is d by dt, dr by dt, that is d2r by dt square. So now let us apply this equation in case of uniform circular motion. So let's say you have a circle and at any instant of time your angular velocity is omega, that is at a time t, if you make the angle theta here, if you move from a position here to here at any time t, let's say time start here t equals to 0, and at a time t you move here, at a time t you have the position theta and t, let's say, which is equivalent to, if the angular velocity is omega, then theta is defined as omega t and t, if you have the following this coordinate. Now what is the position vector of particle at an instant time of t? So this is x and this is y. If you take the projection here, you will get x is if it has length, this vector has length r, the radius of this circle is r, the particle is moving in a circular motion with radius r, then this thing is x is r cos theta, and this projection is the y coordinate, the y component is r sin theta, right? So now r, the position vector r is x cap plus y cap, right? So r is like, and at a time t, that is cos omega t, and r sin omega t. So r is at r cos omega t x cap plus sin omega t y cap. So what about mod of r? We already know mod of r is r. Let us verify from this relation. So r is, since r is a scalar, you can put it outside. Then mod of cos omega t x plus sin omega t y. Since that is r cos square omega t plus sin square omega t, that is 1, so that is r. We just verified this formula. So now what is the velocity of that particle? For velocity, you need to take the derivative of r with respect to time. Since r is not changing, we have r, we can pull r outside, and this gives you omega sin omega t x cap plus cos omega t into omega y cap, that is r omega minus sin omega t x cap plus cos omega t y cap. So this is the velocity vector. Now if you take the dot product with velocity with the position, you will get r omega minus sin omega t x cap plus cos omega t y cap dot cos omega t x cap plus sin omega t y cap. the first, so it will give you r omega minus sine omega t cos omega t plus these two terms and these two terms. Other terms will be 0 from the cross correlation since x dot y is 0 plus sine omega t cos omega t, x dot x is 1 and y dot y is also 1, that is 0, that is p dot r is 0. That means p and r formed a right angle to each other. That means at any instant of time, if you have velocity, if you have a vector r and the velocity vector will be directed along, that is the x coordinate minus and y coordinate is plus. So the only way that x coordinate will minus and y coordinate will be plus here is in this direction, not in this direction, because here x coordinate will be plus and y coordinate will be also be plus. So in this direction, and it will form a right angle to that position vector, right angle with the position vector. Now what about the acceleration? In order to calculate the acceleration, you have to take the dv by dt. So dv by dt is basically here r omega square minus sine minus cos omega t x cap minus sine omega t y cap, that is minus r omega square r cap, right? Minus r omega square, let's say this is r cap since r is r cap. So r cap is the normal r cap is the unit vector along r. So a is minus r omega square r cap. So the direction of acceleration at this moment is in the negative direction of r, that is direction inward. So that this inward acceleration is known as centripetal acceleration. So in conclusion, a body in a circular motion always feels an acceleration that is inward to it in its frame, and the position vector of that particle is right angle to its, and the velocity vector to its particle is right angle to the position vector. If this is r, and this is the direction of v, and this is the direction of acceleration. It is the centripetal acceleration that causes the body to move in a circular motion. So in the next upcoming lecture, we'll generalize this motion to any varying radius, that is r is also not constant, that r is also varying with time. Then what happens? Then what is the most generalized motion in case of moving body in vectorized form? So here r is also changing, theta is also changing, unlike the previous scenario. In the previous scenario, r is constant, but theta is changing, that is circular motion. But here it is the most generalized motion because the r is changing. So we'll analyze this scenario, what will be the velocity and what is the acceleration, and what can be the all the possible problem arises due to this motion. So we'll discuss all this in the upcoming lecture. Thank you.